It's truly astonishing to see the prime directive from the Star Trek universe referenced in a peer-reviewed scientific paper. And yet, this model seems to offer a compelling answer to the Fermi Paradox. In the Star Trek universe, the first rule is clear: never make contact with a civilization that has not yet reached a certain level of technological and cultural development. The theoretical father of the atomic bomb, Nobel Prize-winning physicist Enrico Fermi, once asked during a lunch with his colleagues, "But where is everybody?" And thus, the Fermi Paradox was born. Despite being 13.8 billion years old and spanning 93 billion light-years, the universe remains eerily silent. This silence has long been one of the greatest unresolved mysteries in cosmology, until now. A recently published scientific paper claims to offer a robust, mathematically grounded answer to why we haven't found aliens, or why they haven't contacted us. Some might say, maybe aliens simply don't exist. And perhaps they're right. But according to astrophysicist Frank Drake, whose famous equation is still respected within the scientific community, there should be at least 5 intelligent civilizations in our own galaxy alone. When we consider parameters such as the number of stars, the lifespan of stars, and the probability of intelligent life forming, the math suggests that 5 civilizations is a conservative estimate. Now factor in that there are approximately 2 trillion galaxies in the observable universe. According to some estimates, that would mean there could be up to 10 trillion intelligent life forms in the cosmos. So here's the real question. If the math says they're out there, why hasn't SETI found anything? Despite scanning the skies in meticulous detail, the silence remains. According to the co-authors of the paper, 2 scientists from Harvard University and IBM Research, the reason why these countless civilizations haven't contacted us is not because they don't exist or can't communicate. The real issue might be that we simply don't yet understand the communication that's already happening. The films Contact and Arrival explore this very idea beautifully. Highly recommended. Humanity's efforts to communicate with extraterrestrials were institutionalized with the SETI program, Search for Extraterrestrial Intelligence, which took shape under the guidance of Carl Sagan. Since 1984, SETI has systematically scanned the skies with dozens of radio telescopes, searching for signs of intelligent life. In addition, the Voyager 1 spacecraft, launched in 1977, carries a plaque with our galactic coordinates and basic information about humanity, just in case an advanced civilization is still trying to find us. It's truly impressive that we can still receive signals from Voyager 1, which officially exited our solar system in 2012. That spacecraft is now so far away that its radio signals, traveling at the speed of light, take 22.5 hours to reach Earth. Although revealing our location might not have been the wisest idea, it's clear that modern human attempts to reach aliens still rely heavily on radio waves. And this is precisely what the scientists behind the paper question. It's worth noting that the paper is far from a pop science piece. It is packed with rigorous mathematics. If you have the time, I highly recommend giving it a read. According to the publication, it's highly unlikely that an advanced civilization would still be using radio waves. Why? Because radio waves lose power over long distances, are vulnerable to interference, and spread widely, making them inefficient and lacking in privacy. To illustrate this energy decay, the authors present a striking calculation. If you send a 1 gigawatt radio signal a billion watts to a planet just 10 light years away, by the time it arrives, the signal strength drops to about 10 to the power of minus 24 watts per square meter. That's the energy level of a virus. On Earth, we have neither the transmitters powerful enough to send such signals, nor the telescopes sensitive enough to detect them at such low levels. This makes radio communication, at a galactic scale, both energetically inefficient and strategically risky. Remember the novel The Three-Body Problem? A single radio transmission led to Earth's invasion. Perhaps our silence is our only shield. Looking at the topic from the perspective of humanity's own communication evolution, in the early 20th century, radio waves were the standard for long-distance communication. But today, critical information, ranging from banking to defense, is transmitted through fiber optic cables, which are directional and encrypted. Some countries have even begun experimenting with quantum technologies, such as quantum key distribution, or QKD, to make communication even more secure and virtually undetectable. In fact, in 2025, the first quantum key was transmitted between 2 separate quantum processors using quantum entanglement. However, we're still far from sending something as basic as a text message via quantum communication. According to the three-stage Kardashev scale, our civilization sits at only level 0.73. In other words, we're just crawling. And yet, even at this early stage, we have already begun shifting towards safer, more private, and more efficient methods of communication. So it seems only logical that an advanced extraterrestrial civilization would follow a similar path. In fact, humanity has already taken small but meaningful steps in the direction proposed by the paper. The problem with radio signals isn't just about signal degradation, it's also about precision. Quantum communication offers highly targeted delivery, where information is sent only to the intended recipient and cannot be intercepted by anyone else. It can be aimed at a specific location, for example, a satellite orbiting planet Z around star Y in galaxy X, 10 light-years away. This way, information is not scattered randomly throughout the cosmos, but delivered directly to the address. According to the paper, when quantum light is directed at a specific region, its divergence angle, the spread of the beam, is extremely narrow. For example, if a beam of photons with a wavelength of 1.55 microns is emitted from a telescope with a diameter of 1 meter, it will spread only over a tiny area of space, nanosteradian scale, depending on the distance to the target. To explain steradians simply, it measures how much of the sky an object occupies. 1 steradian corresponds to 1 square meter of surface area on the surface of a unit radius sphere. A nanosteradian, then, represents just 10 to 9 square meters, a vanishingly small patch of sky, making it incredibly difficult to detect by unintended observers. In summary, the authors argue this. Classical radio signals are like tossing confetti into a field. It scatters everywhere. But quantum light is like a laser pointer. It travels only to where you aim. And this cone of light is so narrow that no passing civilization could intercept it by chance. That on a galactic scale, if your signal is accidentally picked up by the wrong civilization, it could mean not only the failure of your communication attempt, but also the end of your existence. That as shown in fictional works like the three-body problem. A captured signal may represent not just a technological risk, but an existential threat. Now imagine this scenario. A highly advanced civilization in our closest neighboring star system, Proxima Centauri, wants to contact us but doesn't want to reveal its location. In that case, it definitely wouldn't use radio waves. What would it do? According to the paper, a signal from such a civilization would most likely be based on quantum entanglement, a directed photon transmission using quantum principles. Unlike radio waves, this signal would be aimed with an extremely narrow beam toward a specific target. For instance, if single photons with a wavelength of 1.55 microns are emitted from a 1-meter-wide telescope, the beam would spread into only a nanosteradian cone, depending on distance. This ensures the signal reaches only the intended recipient. However, in order to detect such a signal, Earth-based telescopes must be aimed precisely and possess extremely high sensitivity. Right now, the largest telescope we have is China's 500-meter fast array, but according to calculations in the paper, receiving such a quantum-level signal from another star system would require a telescope with a diameter of at least 100 kilometers. This, the authors claim, may be the real reason we haven't received any alien messages. In fact, the requirement of a 100-kilometer telescope introduces a new explanation for the Fermi Paradox. Here's the paper's proposed solution. If advanced alien civilizations communicate via quantum channels, their signals must be directed with such extraordinary precision that only a massive telescope at the receiving end could detect them. And since these advanced beings would almost certainly possess the resolution to see that we don't have such a receiver yet, they simply wouldn't bother sending us anything until we do. So, under the assumption that interstellar communication is quantum-based, this alone may be a sufficient explanation for the silence. But how realistic is this idea? That's where the real debate begins. The feasibility of this proposal hinges on whether quantum entanglement can persist over interstellar distances. To date, the farthest successful entanglement experiments have reached only around 200 kilometers. Whether such entanglement can remain intact across 4 light-years, that's the real test. However, a 2020 publication from the University of Edinburgh has shown, at least theoretically, that quantum entanglement can persist across galactic distances. Therefore, the idea proposed in the paper does find support, at least on a theoretical level. Subscribe to our channel and be the first to know when new scientific papers like this drop.